Hey y'all! So in today's video, we will continue our Python for Data Science series and discuss tuples. More specifically, I will go over an introduction, discuss how to create tuples, tuple properties, how to access tuple elements, tuple operations, tuple methods, nesting and unpacking tuples, tuple use cases in data science, common mistakes and pitfalls, advanced tuple usage, and some practical examples. As always, this video is timestamped, so if you'd like to skip to any of those specific sections that I just discussed, feel free to do so by clicking on the timestamp in the description. So let's get into it and let's tech talk with Tyler. Tuples are a fundamental data structure that is useful in many programming and data science tasks. Let's break down what tuples are, compare them with lists, and then discuss the importance of their immutability. A tuple is an ordered, immutable collection of elements. This means that once a tuple is created, its elements cannot be changed, added, or removed. Tuples are similar to lists in that they can store multiple elements and are ordered collections. However, the key difference is that lists are mutable, which can be modified, while tuples are immutable and cannot be modified. So lists are defined using square brackets, while tuples are defined using parentheses. Immutability is an important concept in data science and programming. When data is immutable, it cannot be changed, which helps ensure data integrity. This is particularly useful for fixed data sets that should not be altered during program execution. Using tuples can prevent accidental modification and maintain the consistency of data. We define a tuple named my_tuple containing the elements 1, 2, and 3. We also define a list named my_list containing the elements 1, 2, 3. The difference, the parentheses versus the brackets. So based on the code snippet shown, we try to change the first element of my_tuple to 10, which raises a type error because, as we discussed, tuples are immutable. We change the first element of my_list to 10, which works perfectly fine because lists are mutable. As we discussed, immutability in tuples help prevent accidental data modification, ensuring data consistency and integrity. This is especially important in data science, where fixed data sets should remain unchanged. Tuples are an essential data structure in Python, and understanding how to create them is crucial. So therefore, let's break down the syntax for creating tuples, see examples of tuples with different data types, and learn about the special cases of single element tuples. So we now know that tuples are defined using the parentheses. Elements inside the parentheses are separated by commas. Tuples can store elements of a different data type, such as integers, strings, floats, and booleans. So on the screen is an example of a tuple named mix_tuple with these mixed data types. We have 1, apple, 3.14, and true. So let's say you want to define a single element tuple. How do you do that? You have to include a trailing comma after the element. Without the comma, Python will interpret the parentheses as a regular expression or just a value grouping. So here's how to create a single element tuple. The single element tuple on the code snippet. Creating a tuple with multiple elements. We define a tuple named my_tuple containing the elements of 1, 2, and 3. To create a tuple with different types, we define a tuple named mix_tuple containing elements of different data types. We have the integer, the string, the float, and the boolean. And to create that single element tuple, we define a tuple named single_element_tuple containing a single element, 42. The trailing comma is necessary to differentiate it from a regular value enclosed in parentheses. So you may be wondering, why is the comma required again? Remember, without the comma, the expression 42 would be interpreted as the integer 42 enclosed in parentheses. So the comma just tells Python to treat it as a tuple with one element. On the screen are some more practical examples of single element tuples. Understanding how to create tuples and the special cases of single element tuples is essential for using this data structure effectively in your programs. Tuples are a fundamental data structure in Python, and understanding their properties is crucial. So let's break down the concepts of immutability, hashability, and the performance differences between tuples and lists. Immutability, hashability, all these terms. So immutability explained. Tuples are immutable, meaning their elements cannot be changed after they are created. This immutability ensures that the data remains constant throughout the program, which can help prevent accidental modifications. Tuples are also hashable, meaning that they can be used as keys in dictionaries or elements in sets. Hashability just implies that the tuple has a fixed hash value that doesn't change, making it suitable for use in data structures that rely on hash values. Lists, on the other hand, are not hashable and cannot be used as dictionary keys or set elements. And by the way, if you're not sure of what a dictionary is, I do have a video on that, and that's linked down in the description. So due to their immutability, tuples are generally faster than lists. This performance benefit makes tuples a better choice for fixed data that does not need to be modified. Lists are just more flexible because they are immutable, but this flexibility comes at a slight performance cost. So it's up to you on which one you use, just see which one works best based on your specific scenario. We use the tuple as a key in the dictionary, which works because tuples are hashable. The dictionary displayed on the screen contains the tuple 1, 2, 3 as the key with the value. So understanding the properties of tuples such as immutability, hashability, helps us in making informed decisions on when to use tuples versus lists in your programs. Tuples provide performance benefits and data integrity, making them valuable in various applications. Let's break down how to use indexing, slicing, and negative indexing with tuples. Indexing allows us to access individual elements in a tuple using the zero-base indices. So the first element has an index of 0, the second element has an index of 1, and the third element of 2, and so on. So slicing allows us to extract a subset of elements from a tuple, very similar to a list if you watch my list video. So the syntax is tuple open bracket start colon stop close bracket, where start is the index where the slice begins, inclusive, and stop is the index where the slice ends, exclusive, similar to lists. On to negative indexing. Negative indexing allows us to access elements from the end of a tuple. The last element has an index of -1, the second to last index of -2, and so on. So for the indexing in tuples example, we use my_tuple open bracket 0 close bracket to access the first element of the tuple, which is 1. For the slicing tuple example, we use the my_tuple open bracket 1 colon 3 close bracket to extract a subset of elements from the index 1 to 3, excluding 3. The result slice is 2, 3. For the negative indexing example, we use my_tuple open bracket -1 close bracket to access the last element of the tuple, which is 5. These techniques allow us to efficiently access and manipulate elements in tuples. Indexing provides direct access to individual elements, slicing enables us to extract subsections of the tuple, and negative indexing lets us easily access elements from the end of the tuple. So you may be wondering, what are some tuple operations? Are they similar to list operations? They are. So let's break down how to concatenate tuples, repeat elements using multiplication, and perform membership testing with in and not in. We can concatenate or combine two tuples into a single tuple using the plus operator. This operation creates a new tuple that contains all the elements from both original tuples. We can repeat the elements in a tuple a specified number of times using the asterisk operator. This operation creates a new tuple with the repeated elements. We can check if an element is present in a tuple using the in operator. Similarly, we can check if an element is not present using the not in operator. Concatenation helps in combining tuples, multiplication allows us to repeat elements, and membership testing helps in checking the presence of elements. So let's break down the count and index methods and discuss the limitations of methods due to the immutability of tuples. So the count method returns the number of times a specified element appears in the tuple. This can be useful for analyzing the frequency of elements in a tuple. The index method returns the index of the first occurrence of the specified element in the tuple. If the element is not found, it'll raise a value error. So as we know, tuples are immutable, meaning their elements cannot be changed after creation. So this immutability limits the number of methods available for tuples compared to lists. Tuples focus on methods for element access and counting rather than modification. So unlike lists, tuples do not have methods such as append, extend, remove, or pop, simply because they're immutable. So on the screen are some examples of tuple methods, including using the count method and using the index methods. These methods are useful for analyzing and accessing elements in tuples, while immutability ensures data integrity and consistency. A nested tuple is a tuple that contains another tuple as its elements. This allows for the creation of complex data structures. To access elements in nested tuples, we use multiple indices. Each index corresponds to a level of nesting. Unpacking tuples allows us to assign tuple elements to variables using multiple assignment. This makes it easy to work with tuple elements individually. We can also unpack nested tuples into variables. This operation involves multiple levels of unpacking to assign all elements to a variable. So on the screen are some examples of nesting and unpacking tuples, including creating nested tuples, accessing nested tuple elements, unpacking tuples, and unpacking nested tuples. These techniques allow us to efficiently create and work with complex data structures using tuples. Nesting and unpacking tuples provide flexibility and ease of use when handling hierarchical data. It's hard for me to say that. I don't know about you guys. So let's break down how to use tuples for storing fixed collections of data as dictionary keys and for returning multiple values from functions. Tuples are ideal for storing collections of data that should not change. And since tuples are immutable, the data remains constant, ensuring data integrity. This is useful for fixed coordinates, configuration settings, and much more use cases. Tuples can be used as keys in dictionaries because they are immutable and hashable. So this allows us to create complex keys composed of multiple elements. Functions can return multiple values as a tuple. This is useful for returning related data from a function in a single return statement, as shown in the get_min_max function code snippet. So let me explain the code snippet in detail. We store fixed geographic coordinates in a tuple named coordinates. We create a dictionary with a tuple that has John Doe as a key. This allows us to use complex keys in our dictionary. We then define a function, get_min_max, that returns the minimum and maximum values from a list as a tuple. We then unpack these values into min_val and max_val variables. So what are some practical use cases? Number one is storing fixed data. We can use tuples for fixed data that shouldn't change, such as geographic coordination, configuration settings, or fixed sets of values. Another one is complex dictionary keys. As we just went through that example, we can use tuples as keys in dictionaries when we need to create complex keys composed of multiple elements. We can use tuples to return multiple related values from a function, making it easy to pass around groups of related data. So understanding these use cases help you leverage the power of tuples in your data science project. Tuples provide immutability, hashability, and a convenient way to handle multiple values. So to the side are some key practical examples that you can review, including creating a tuple of coordinates, using tuples in lists and comprehensions, and swapping variables using tuples. These practical examples demonstrate the versatility and usefulness of tuples in various programming scenarios. So I suggest you pause the video and look at the code snippets for more insight, and then press play so you can continue watching. So let's break down common issues like mistaking tuples for lists, trying to modify tuple elements, and dealing with single element tuples. So a common mistake is confusing tuples with lists. Remember, tuples use parentheses while lists use square brackets. It's important to use the correct syntax to avoid errors. Tuples are also immutable. So if you attempt to modify tuple element, it will raise an error. Defining a single element tuple requires a trailing comma. So without the comma, Python will interpret the parentheses as just a regular expression or grouping, not a tuple. I have included some examples of common mistakes in Pitfalls and suggest you pause the video to understand some more. Understanding these mistakes can help you avoid errors and tuples and use tuples effectively in your programs. All right, name tuples. This is a powerful feature and type in Python that allows us to access tuple elements with names, making our code more readable and self-documenting. So let's break down how to create named tuples, their advantages over regular tuples, and examples of named tuples in data science. Named tuples provide a way to access tuple elements using names instead of indices. This makes the code more readable for both you and other people reading it, and easier to understand. We can create named tuples using the named tuple function from the collections module. So as we already said, named tuples are just more readable and self-documenting compared to regular tuples. They allow us to access elements by name, which makes the code clearer and less error prone. For example, in the code snippet, we created a named tuple point with fields X and Y. We then create an instance P and access its elements using names. I have another issue saying access. Named tuples can be used wherever regular tuples are used, but provide the added benefit of named fields. So to explain, we create named tuples, record, and coordinate to represent structured data. This is useful for handling data in a clear and structured way. Some key points to remember. The first is readability. Named tuples make the code more readable by allowing access to elements using descriptive names. Also, self-documenting. Named tuples provide a self-documenting feature, making it clear what each element represents. Also, versatility. Named tuples can be used wherever regular tuples are used, but offer the added benefit of named fields. Understanding these advanced uses of tuples helps you leverage the power of named tuples in your data science project. Named tuples provide a clear and efficient way to handle structured data. That's all I have. I hope that by now you have a better understanding of Python tuples than you did a couple of minutes ago. If you have any questions, comments, or even any more Python topic suggestions, please leave a comment down below. Also, if you haven't already, subscribe to my channel and click the bell icon to be notified whenever I post another video. Thanks for interacting with Tech Talk with Tyler, and I'll see you later.